So these are the so-called variational formulations. And classically, the term variational formulation referred to constructing a functional or a variational principle. So this is essentially what we did. That is equivalent to the governing equation. All right, so this is what we did was sort of the classical variational formulation. Okay, but the modern use of the term variational principle refers to a formulation where the governing equation are translated into an equivalent weighted integral statement. All right, so I think this is what you were sort of getting at. And so, weighted integrals. Or weighted integral statement. So yesterday, or last class, when I introduced the finite element method, I said, in the finite element method, we're going to seek a solution U that's approximated by U of H that is summation of some unknown approximate functions times unknown locations of U at nodes, right, plus summation of some different approximate functions at some locations that aren't necessarily associated with the nodes, right? So Uj is nodes associated with the nodes, right? But at this point, I haven't talked about any kind of discretization technique, right? So we don't have nodes. So we have no nodes. So for now, we're just going to have that U, which is approximated by U of H, is equal to J equals 1 to M Cj phi j. And I have a phi 0 here. And the sole purpose of phi 0 is to satisfy the boundary conditions. So I don't want to imply that this is any different than that. I mean, if I change this summation from j equals 0 to m, then I have phi, the first term would be phi 0 c0. Well, so I'm just saying that c0 is 1, and so then I just have this phi 0 there. Okay. So it's not really anything different. I guess I would say j equals 0, m minus 1. But yeah. These two things are the same if I have no nodes. I just pulled that constant term out and said that this constant term is associated with the boundary conditions.